Hi everyone. Is the mic picking me up okay? Yes, great. Okay. So thanks so much for hanging out on a late Wednesday night here to see all this. So I just want to give a quick little background. So I discovered Haskell, or Haskell sort of discovered me in 2011. So there's probably a few people here who've been doing Haskell longer than I have, actually. But then through a series of pieces of good luck, ended up sort of embedding myself into the compiler. So now spend either not enough time or way too much time, depending on how you count, hacking on GHC and implementing a bunch of things. So we'll see that in a sec here. So before we get into the actual subject of my talk, I just wanted to give the brief history of what Haskell has done with types. And so Haskell has lots of other cool things to it, but I'm really just going to be focusing on types. That's my area of interest. So it has type classes, right? That was a really new and wild idea when it came in 1989. This was right at the birth of Haskell. And that came in so that you could write show and have it work on many different types, right? No one had really figured out how to do that in a good way. So then, slowly things are growing, right? The beginning is always slow. And we got functional dependencies in 2000. And one thing we're going to see on this slide, all of these type innovations are part of our published pieces of research, which I think is another really awesome thing about Haskell, is that we're a research language, and yet there's a lot of people in this room, some all, using it to make money. And so I think that's a really interesting place to be. So we got functional dependencies, and this is where we started to realize that types can do some really cool things. We added data families and type families in a back-to-back year from Manuel Chakravarty and his collaborators, where we can now have a different way of computing on types. And actually, data families, the original motivation was to make programs run faster. It was all about optimization. And all this other stuff was just, oh, cool, we can do other fun things with types too, other than just optimization. So GADTs came along. We're going to see a lot about that tonight. So if you haven't seen those, then you'll see a lot of that tonight. GADTs, by the way, stands for generalized algebraic data types, but that name isn't helpful. So then I think there was a lot of ferment in there, a bunch of new features, and it took some time for all of that to settle and get all the bugs out. And then now we're sort of in a new period of ferment, starting with data type promotion. So in 2012, now we could start using our data types as kinds. And we'll see a little bit of that in this talk. But that sort of started this new revolution in types. So then this is when I started my Haskell journey. And so you'll see the papers that I'm involved in, sort of a slightly different color over there. So I wrote the singletons library, which allows you to pretend like Haskell has dependent types in a terrible, awful way. So I wrote the library. Actually, now a collaborator of mine, Ryan Scott, does most of the maintenance for it. But I sort of hate it. It's terrible. It's the best thing we've got, though. And so what we'll see is one thing I'd like to do is get rid of that and actually replace it with the real thing. It's sort of doing it the fake way. Then we wrote a paper. The actual Haskell implementation didn't come for years later because it was really hard. It took a long time. But we have type in type, which is this obscure feature that came with GHC 8.0 that nevertheless took 20,000 lines of Haskell code to implement. And we'll see a few applications of that today, but it totally reworks the internals of how Haskell's type system works and is a necessary stepping stone toward dependent types. So I'll circle back to that a few times. So then there's closed type families. So this now takes type families and makes them a little bit more like functions. We have new GADT pattern match checking. So when you do pattern matches, now you can rely on them more than you could before. We have injective type families that allows you to do more type level reasoning with your type families. Type application allows you to use fancy type things in a slightly easier way. We have the new typable. Typable keeps on getting reinvented, and it's not done being reinvented. I know what the next version is going to be. So that's the new feature that's going to feature in our talk tonight. Pattern synonyms, which allow you to take this idea of a pattern and abstract over it. This is totally unique to Haskell, and at least as far as I know. and I think a really powerful feature. We learned a lot about types just learning about patterns, actually. And the future continues. So quantified class constraints, this is a paper just last year. Simon Peyton-Jones implemented it in a rainy weekend this winter, because that's what he does on rainy weekends, right? So this allows you to have a for all in a constraint. So we're not going to have a big example of that tonight, but that's on its way into GHC now. And so this continues, and you know, in 2 years, maybe when I come back, or next year, whenever, there's going to be more papers to add to this list, right? Haskell is developing really quickly. There's a lot of innovation here. Now, I just want to call out, in the last talk, the folks from Summit were talking about how they wanted to avoid using all of this stuff. And I appreciate that point of view, and they might be right. I think they are probably right. This is the more researchy end of the language. This is going to change faster. This is going to be things that we did wrong, right? So closed type families, right? That's my name over there. There's a lot of things about that that's wrong, and so maybe you know, things might change there at some point. Hopefully in a backward compatible way, but. You know, all this stuff is happening, and yet it's still a language that can be used in practice. And so, again, I think that's a really cool thing. Okay, so all of this is enough to make you go crazy, right? And so, one of the goals of my talk today is to allow us to step back a little bit and figure out how we can use some of this technology. And so, this talk is going to be a long example of how a bunch of these different features can all work together to do something pretty cool. So the thing that we're going to do is write this stitch, right? So stitch stands for sound type indexed type checker. But the idea is it's the implementation of a simple lambda calculus. So often when programming language folk like me talk about implementing the lambda calculus, right, there's sort of a groan and it's like, oh, can't we come up with something more original than that? I want to turn that around and say, yes, we can come up with more original things, but we're better at this, right? This is what programming language people do as we think about the lambda calculus. So this example is going to be better in that way. The other thing that's really nice about it is that functional programmers will understand this example. I don't have to spend half my talk building up what my example is supposed to do, because we all know Haskell, which is some variant of the lambda calculus. And it's a practical application in that most real programs have to have an implementation of some language somewhere. There's some configuration file that gets read in somewhere that maybe has some processing. Or, you know, if it's a web browser or something that interacts, maybe it has to process some JavaScript. Every Office utility tool has some language that it has to process. Every data visualization tool has to have some language that it has to process, right? This is a practical example. It's not just introspective, but it's practical. The code that we're going to be looking at is available. You're welcome to take it out and download it and sort of poke around. I'll be sort of telling you what file to look at. Doesn't look like a lot of people have laptops out, so that's fine. Everything will be up here. You certainly don't need to do that. Okay, so let me demo what it is I'm talking about here. Get out of Keynote. So here's, no. I see something different here than you see there. Uh-oh, zoom.us quit unexpectedly. Okay. I'm going to, if anyone has the meeting number that we're in, I'm going to need that if we want the presentation to continue. Sure. Right, yeah. With types, this can't happen. Okay, 110. Yeah. Okay. That would be nice. Okay, there is an awkward shot of me. Let's see, join audio conference. Mute. Oh, no, bad. Stop video. Share screen. Okay, we're back to that. Will it go over to Emacs? Will it go over one more? Yes, it will. Okay, I'll go slower now. Maybe Zoom.us doesn't like it when I change screens too fast. Okay, so here's Stitch. Hopefully this is big enough for everyone in the back. Yes. Okay. And so this is a basic lambda calculus interpreter. It is one where you have to write your types in. I think actually since finishing this, I figured out a way to get type inference to work in this system, but we're not there yet. So I can do something like this. I can say, I can define a function where x is an int, and we compute x plus 6, apply that to 3, aha, it's 9, right? But it's a full lambda calculus, so I can do something like this. Here's a function that sort of does reverse application, but twice. And so if I do this, z plus 4, hopefully this should print out 13? Yes, there it is. Okay, right? So this takes an int and a function, and it applies the function twice to the int. Okay, hopefully no big surprises. But this is useful for more than just this. If I want to actually learn a little bit about lambda calculus, I can tell it to step and show every reduction step according to a call by value lambda calculus. One thing that we see here in this example is that when it prints out a function, it prints out using a technique called de Bruijn indices, which we're gonna explore in a moment. But you can follow the colors, right? So this 0 is going to refer to the variable that's bound there. So, but just add a quick question here. How many people in here have heard of de Bruijn indices? Oh, wow. That's way more than I expected. Okay. And so I think colors is actually a really good way to do this, right? Because the problem with de Bruijn indices is that depending on where you write them, they mean different things. But this is set up so that the colors stay the same. And so we can watch the reductions. So this might be useful for, say, teaching lambda calculus if that's something you ever want to do. That's enough of the demo. Let's go back to the slides. Uh-oh, I did that fast. Okay, but it's okay. And we will play. Okay, so here's a quick introduction to de Bruijn indices because this is going to be something that we have to revisit a few times during the talk. This is really what the definition is here. So instead of remembering names of bound variables like x and y, which in the end don't matter at all in a lambda calculus program, we just use numbers. And so here we can see that this 0, that corresponds to the variable that was bound there, because there are 0 intervening binders. And the 1 here corresponds to that variable bound there, because there's 1 intervening binder, right? Where this is the intervening binder. And that's what de Bruijn indices are. It's a different notation for variables that means we don't have to come up with names anymore. And so that's going to correspond to how we would write it more naturally. So an easy question right now is, why do this? So there are several answers. So we don't have to worry about shadowing anymore. Right, so shadowing is when you have multiple variables, all of the same name, but there's one that's more local than the others, and that's really the one you mean, and that can be awkward in a language implementation. As I said, the names are meaningless anyway, right? So it sort of removes information that we don't need, and it's easier to work with in the computer. The reason not to use de Bruijn indices, the only one that I can really come up with, is that they're hard for humans. But I think that we can get around that by certain encoding techniques and things like colors to make it easier for us silly humans, right? Computers like these, humans don't so much. But that's the choice that we're making here. What our goal is, what the interesting thing is in Stitch, is that internally the way that I represent one of these lambda calculus expressions is using this data type x. I'm not expecting you to understand most of this right now. We're going to come back to it. We're going to build up to this actually. But is to use this data type x that can only hold well-typed expressions. So here, for example, we can see, again, just sort of blur your eyes a little bit. It's okay if you don't understand the details. But here, this is how we represent an application of a function to an argument. And we're going to say that the function has type arg arrow res. The argument has type arg. And the result is going to have type res, right? If the function argument doesn't match the actual supplied argument, it's not going to work, right? So the goal here is that only well-typed expressions are representable in the interpreter, And so that means that any manipulations that we do over these expressions have to be type preserving. We can't possibly write something that goes wrong here. And that's going to really help in our implementation of the interpreter. Okay, so I said we were going to build up to that because can we actually do that? How do we know when the user types in a program that it's well typed, right? So we can't just directly parse into something that fancy. And so a lot of what we encounter here is going to be building up to something that glorious, sort of step by step. Okay, so the first step in that direction is this a length indexed abstract syntax tree. So this is what we're actually going to parse into. The U here stands for unchecked. And I'm going to use a convention throughout the talk of colors, right? So this blue, that's a Java keyword, right? Green is going to be a type. Purple here, my daughter told me it was pink. I still think it's purple. Is going to be a kind. And then this burnt umber, perhaps, is going to be terms. So that can help us sort of keep straight, right? I always find this syntax in Haskell confusing, that we have terms right up next to types when we declare data types, but that's what we do. So the idea here is that this is a much simpler data type. So here in the application, right, we just have some expression applied to some expression. There's no types yet, because we're going to have a separate type checking pass that gets us, from this representation to that other one that we saw a few moments ago. What is interesting here, though, is that what we are saying is that this expression type still keeps track of how many variables are in scope. Because it turns out that as we parse a lambda-calculus expression, we always know how many variables are in scope. Every time we see that backslash, we can say, oh, there's one more variable in scope. And so because we can do that while we're parsing, we can put that information here. So this n, this index to my type, right, type parameter, tells me how many variables are in scope. And so normally for a data type like maybe, we have something like data maybe A, and that's some other type. Here, though, instead of it being a type, it's a natural number, right? It's going to be a number 0 or greater. Those are the number of variables that are in scope. Here, in a lambda expression, we need to know the type of the thing that's bound. We don't need to know its name, right? Because there's no names anymore. There's just these numbers. So we don't have to have that here. And then we have some other expression, but of course that other expression has one more bound variable. So this suck is short for successors. That's the next natural number up. Here in an application, both the function and the argument are in the same context, so there's the same number of bound variables. So we see n and n there. In a let, we're binding some new variable. That's going to have the same number of bound variables. But then over here, this is the in part. There's one more bound variable. So we see successor over here. I think actually, OK, so what's going on up here is that in a variable, we need to store which variable it is. So this is going to have to be some number, 0, 1, or 2. It's one of these de Bruijn indices. And so we'll come back to that in a sec. I think I have a few more sort of explanations in here that I already described, right? But what I want is, if I know the number of bound variables, then I really want this type to only be numbers that are less than that number, right? If there are 2 bound variables, keep doing that. If there are 2 bound variables, then I can have a de Bruijn index of 0, or I can have a de Bruijn index of 1, but I can't have a de Bruijn index of 2, and I certainly can't have one of 10. Right? So I want to build my data type to avoid the possibility of that. So that way, when I do variable lookup, I'm guaranteed that variable lookup will succeed. So that's what fin is all about. So fin is short for finite set. So let me just do a check on type level. How many people have seen fin before? OK, so fewer than before. OK, but still quite a few. So the type fin n contains exactly n values. That's the usefulness of it. So when I say fin2, that's the type for de Bruijn indices when there are 2 variables in scope. So there's only 2 possible values, 0 and 1. So here's the definition. So first we define natural numbers using Peano natural numbers. And so, right, so every natural number is either 0 or the successor of some other natural number. We can eventually build up to any number greater than 0 that way. And if you start getting worried about, space concerns and such, that can all be fixed. I'm not worrying about it in this talk, but if you want, we can talk later about how to avoid efficiency problems with that. Here is the definition for the fin type. This one's, I think, rather hard to understand. So I'm gonna do a few examples here. So here, Z stands for 0, S stands for successor again. This is essentially a different encoding of natural numbers, but it's an encoding that is bounded. We can't ever get higher than a certain value, essentially. So I can say that Fs of Fz, right, this is a representation of the number 2, has type fin 5, where I've written the number 5 here instead of suck 0, right, because that would take too much space on the slide. And the way that that works is that whenever we say Fz, that's fin of the successor of some number n. And so type inference can actually figure out what that n should be. In this case, it's the number 2, right? Because if Fz, if this n is 2, then this Fz has type fin 3, Fs of Fz has type fin 4, and Fs of Fz has type fin 5, exactly as I wanted. Right? So we see that every time we apply one of these F constructors, we have to increment the index to the fin here. So I can also say that Fs of Fz has type fin 3. And if I say that, type inference will tell us that the n at Fz should be 0, right? Because each of these Fs increments it up to 3. But if I want to have Fs of Fz be fin 2, I'm in trouble. There's nothing I can put there, right? So this notation with this at sign, excuse me, that's the type applications extension, which allows us to specify type parameters in terms. And so here, there's no way of building this, right? Which is exactly what I wanted. I wanted fin 2 to only have 0 and 1, and this is an encoding of 2. So I don't want 2 to have type fin 2. So this is sort of a proof, a suggestion, several examples demonstrating of how this fin works, right? But it really does work. So fin 2 really only has these 2 values. And I do try to be careful. Yes, there's this thing called undefined in Haskell. And that's why I keep saying values, because undefined is not a value. Although I suppose if you want to be pedantic, you could have Fs of undefined, which would be a value. Let's not go there. Laziness has its pluses and its minuses. Okay, so that's what fin is doing. So by having fin here, it's saying that all of the variables in my expression have to be in scope. So later, when I'm interpreting this little lambda expression term, at some point I'm going to have to do variable lookup. That can't ever fail. And so I've encoded an invariant into my type so that later on, if I didn't do this, at some point when I see a variable, if I just had an int here for my de Bruijn index, then there'd have to be some partial function. There'd have to be some function that calls error, or that calls some fail on a monad, say, right? And I don't have to do that now, so my implementation is safer. Okay. So how are we going to parse such an identifier? So part of this is an exploration of, we start with a simple idea of, I want to encode certain invariants in my data structures, and then what does that then cause me to have to do to deal with that first decision? So how do I parse an identifier? So it might be tempting, if I have some parser monad, I'm not going to get really in depth into parser monads tonight, that I could have some parser that returns one of these expressions. It doesn't really work, though, because we don't know what n should be, right? I don't know, as I'm parsing, am I parsing something that's going to be, it's going to only have 1 variable in scope, or am I parsing something with 5 variables in scope? There's not enough information here. Okay, so to demonstrate this, I'm actually going to switch over and look at the code a little bit instead of trying to put it all in slides. So hopefully there's no crashes this time. There we go. Okay, that's big enough in the back? Yes. Okay, no one's complaining. Okay, so I'm using parsec here to do my parsing. So we can remind ourselves of how parsec t works. So parseCT has 4 type parameters. So we have the stream type. This is sort of the input to the parser. In this case, it's a list of located tokens. I'm not going to get all into detail about the tokens here. U is the user state, which we don't use, so I just have unit there. And then parseCT is a monad transformer, so it's building on top of some other monad. The other monad I'm using is the reader monad, which allows me to access some environment. The environment here is a Veck containing strings, right? These are the variable names of the variables that are in scope. Because as much as I like de Bruijn indices in my implementation, remember when I was typing in the demo, I was still typing X and Y and Z. So we need to have the strings that are in scope so we can do a lookup. And so that's stored there, and more about that in a sec. And then of course, A is just going to be the return type of the monadic computation. So, I realize time, the presentations are always hard because there's always trying to pack things in. But I also want to pause. Are there questions? There's probably some people who are completely lost. I know that's going to happen. But if you can identify yourself as only a little bit lost and have a question that can get you and then all those other people who are lost in that same space as you, that would be really helpful at this point. Yes?
Oh, sorry. Is n in type parser n like a value or a type?
That's a great question. Yes. So it is a type in that this whole line is defining a type synonym. So it's part of a type. It's a value in that its type is nat. So it's built up from 0 and suck. In the normal way that we talk about in Haskell, I would say that it's a type, or it could be a promoted value or something like that. I've stopped thinking of these things as promoted and just sort of, that values can flow back and forth between runtime and compile time. So you might want to think of it as a compile time value, perhaps.
That I guess means that it's eager, right?
Is it eager? I wish I could say it were. It's not eager, it's not lazy. Haskell currently has a terrible story about sort of evaluation semantics in types. What was that?
That's in GHC.
Yes. So that is considered only by GHC. When I'm running the program, that's gone. In that sense, it's eager, but it's not quite eager. Other questions? These are great questions, helping to sort of focus on things I may have skipped over.
Could you elaborate a little bit about the fin thing? Like, what's the difference between the fin versus the nat?
Okay, so a nat is unrestricted. A nat represents any number 0 or greater. Fin, whenever we have a fin, we have to say it's fin of something. So it's bounded above. So instead of being any natural number, a fin we can think of as a natural number less than some other natural number.
So it's like a finite set up to n.
It's a finite set up to n, yes.
So in the previous slide, I see you said that you couldn't have a. I was actually quite confused because you crossed it out. But it's like you couldn't have a fin of n, just plain n.
So here, yes. So the problem is here is that we don't have. So this would be some computation that will return one of these expressions that have n variables bound. The problem is that there's no way of sort of knowing at runtime what n is. So we can't make a decision. If we see a variable in an expression, we can't make a sort of a runtime decision on how we should treat it. There's not enough information here. It's a good question, and I've given a bad answer to it, and I know that. I don't have a better one that I can sort of trot out without diving really deep into the code. Okay, I think I'm going to plow forward. So, so there's a new type in here that I want to explore a little bit. Veck, of course, we can't get through a talk of mine without having Veck. So how many people here have seen Veck before, right? This is like the standard example of using GADTs in Haskell. But it's really useful, and that's why we always use it. So let's go over to see Veck. Oops, that's not the part that I wanted. Here it is. So Veck is just like list. At runtime, this is the same thing as our good old friend list. What's different here is that there's extra type information. So what I'm saying here is that every Veck, instead of just taking a type parameter, it takes both a type and a number, and the number tells me how long the list is. So now instead of the normal list type in Haskell, which can have any length, these are only a Veck with a certain length. It only has one particular length. And so I can choose the type of the values stored in my list, and I can also choose the length of my list. So there's two different parameters here. And the way that this is set up is that nil, of course, is going to be a vector. It can contain any type, but nil always has length 0. The cons operator, spelled like that, takes a new element, that's the new head of the list. It takes the tail of the list, which will have some length n, and then it produces another list whose length is one more than the length of the tail. And so in that way, this is encoding the length of the list in the type. And so now I can talk about all lists of length 5. And I know if I design my function to take in lists of length 5, that you can only pass in lists of length 5 and not any other length. And so this, even by itself, without going any further, can be really useful for, say, if you wanted to write a reverse function. You could write a reverse function that takes in a Veck an and returns a Veck an. And if it type checks, because those n's are the same, that means that your reverse can't be dropping or adding elements. Or if it does so, it has to do so in equal numbers or something very silly like that. Okay, here I have another function that we'll see again, we'll see a usage of this in just a moment. This allows us to look up the index of some element of one of these Vecks. Right? So this is the same as the, is it called element index in data.list? Does anyone, or is it just index, I forget, index of maybe, I think it's called. This allows me to look up an element in a vector. And so in data.list, this would return maybe int. But here we can do better. We can say, of course, the index into a length n list has to be some number less than n. And we have a representation for numbers less than n. It's fin. So here, it might fail. Maybe the element I'm looking for isn't in the list, so we still need the maybe. But if it succeeds, I'm definitely going to get some number less than n, which is the length of my list. The implementation here is basically the same as you would write over normal lists, right? If we have the empty list, then that means nothing. We haven't found the item that we're looking for. Otherwise, if we found the item, then we're going to return 0. Otherwise, if we haven't found the item, we can keep searching in the tail of the list as long as we increment the number that we get out, right? And we're here, the functor I'm using is just maybe, right? That's sort of more standard Haskell stuff. Right?
Really decrement?
No. So the idea here is that we've found the element in the tail of the list, and so the elements index in the tail is going to be one less than the elements index in the larger list. Yeah. Other questions?
So using these dependent types, using Veck, does that do anything for the caller of this function? Instead of using algorithms, or is the point of this to save the author of this function from stream?
Yes.
Is there a benefit for the caller as well?
Yes. So the benefit for the caller in this case is that the output that we get, the caller then has a guarantee that it's less than n. Right? So if we didn't use the dependent types, we wouldn't have that guarantee. And so let's jump to the use site, which is, here it is. Oh. So this is the function that parses identifiers in this lambda calculus. And so first we have to read in the name of the identifier, right? That's what this line does. The details of toke prime are really not important. But then asks is a method in the monad reader type class. This is not, there's no weird dependent type stuff going on. This is just monad transformer stuff going on. But the idea here is that there's that environment that I said above where the parser has this Veck of strings, right? These are the names of all of the in-scope variables in our lambda calculus expression. And I want to look up this name I've just read in. And so it will, this asks, allows me to query my environment, and then it's going to return possibly an index. So if it failed, then that means I must be accessing a global variable. I didn't demonstrate that in the demo, but the Stitch interpreter supports globals. If it did find it, then that means I have some index I, and then I'm going to return uvar I. Now this uvar, remember, the argument to a uvar is one of these fin types, right? Because I want to be sure that this de Bruijn index is going to be in the appropriate range. And so all of these types are sort of flowing together to keep me honest. And so that's how it benefits the caller of this as well, because now I can take that and I want my uvar to have the invariant that the de Bruijn index in the uvar has to be less than the number of bound variables. And GHC is proving that invariant for me. Okay, so other interesting things to see in here include the parser for lambda. So that's up here. So of course we read the lambda, right? That's just a backslash. And then we have to get the name of the bound var. Then there's the colon and the type and the dot. And then we want to parse the next expression knowing that that bound variable is bound. So there's this bind function which adds a new bound variable into my environment. And then expr here, it's not on the screen, but that's the parser for expressions. Sort of the top parser that can handle all the different kinds of expressions. So what I want to do now is jump up and look at the implementation and the type of bind. Because bind has to do this funny thing of dealing with, where is it? There it is. Of dealing with the fact that one expression has one more bound variable than another. And so indeed, we have to give it the name of the variable that we're binding so that later lookups can access that. The expression inside is now in a context that has one more variable in scope. So this parser has to work in an environment with one extra element. So we have suc_n here, but then when we're done parsing the lambda itself doesn't have any new variables in scope, right? The lambda sort of is done by the end of it. And so here we're just in an environment that has n variables in scope. So I'm tempted to use, how many people are familiar with the local function of monad reader? Not very many. Okay. More people know Veck than local. This is interesting. I wonder what that says. So if not many people, I'm going to skip over this then, because there's an interesting contrast, but I think if there's other people, I'm looking at my watch, so let me jump into other things instead of going into heterogeneous monads. Okay, so I'm going to pop back to the slides then. Okay, let's see, it's 8:45 here. I was worried that I might run over. I think I might, no, let's do all that. I might skip some of the slides in here, but I think some of this is going to be pretty interesting. So I have to have some representation of types in Stitch. And so the key idea here is that I'm going to use type rep internally. And you know what? I'm just changing my mind because I want to have time for questions, and I know we need to start actually packing up, and we need to be out of here by 9. So I'm going to change course and jump to milepost. There we go. Okay. So actually, most of what we've seen, most of these bullets, we've gotten a chance to hit. So what we see here is that if we want to have this well-scoped AST, we want that invariant that all of the variables are actually in scope, right? But once we start doing that, we have to do other fancy type things elsewhere. So now we need fin to be able to do the well-scoped thing. We had in our parser, we had to keep track of the number of bound variables also needed to be that same n. If I just used a list, things wouldn't work out, right? Because I need to be able to look up in that list and be sure that I'm going to get something less than that bound n. And so this is yet another use case of length indexed vectors. I had to skip over how types require existentials here, but these slides will be made available online and you can check it out there. Okay, so what this is all building up to is all of this. So we still haven't quite gotten there because I haven't told you really what this means, but the idea here is that this exp type is parameterized by two things, a context and a type. And what it really means is that if we have some expression of type exp ctx tie, that means under the typing context, ctx, the expression has type tie. How many people in here know this notation? Okay, fair amount. So that's really what we're after. Instead of encoding just terms, we're really encoding typing derivations. So a context here is really just a vector of types. We need to know the types of all of the variables that are in scope. And so that's going to be a vector of types. And of course, we want to keep track of the length of this thing so that our de Bruijn indices work out. A de Bruijn index is really just an index into this vector. So when I say that I have index number 1, that means that I'm going to get the second element from my vector, and index number 1 has that type. And we can build this up sort of piece by piece. Of course, type is also the type of things that classify value. So like the kind of int is type, right? So maybe some of you haven't seen kinds yet, but if you think about maybe, for example, maybe isn't a type. Maybe it has to be given a type to become a type. So we can think of maybe as something that takes one type and returns another. So maybe's kind is type arrow type. And this is that same type there. And if I'm using type, then that means that this, what I'm calling a type synonym here, isn't really a type synonym, but a kind synonym, right? So what I'm really doing is this is sort of one level up. And I'm seeing some heads nodding, so maybe you've done some of this kind of shenanigans before, because I know I'm going a little quickly right now. Another feature I wanted to sort of point out here is that this is an example of polymorphic recursion, in that I'm describing that this expression works over some context of some length, but actually that length changes in recursive occurrences here. And so because of that, I need to make a cusk. How many people have heard of cusks? Oh, good. Cusks are terrible. I can say that because I was part of the group that invented them, but we're getting rid of them. Okay, so we'll skip over cusks. Once again, we have a de Bruijn index. Let's sort of pop forward a little bit. Here, this is a good slide. So we want to be able to convert you know what? Can't do that slide without doing the two slides before. So we'll just go here, and then that'll probably be about it. So here, we want to be able to take the unchecked expressions and convert them into checked expressions, right? So we need to have some function that goes from one of those things that we've parsed to one of these type checked ones, right? And so this is going to be the type checker. So it's tempting to write something like this, where M is going to be the monad that deals with error messages and all of that stuff. But that type isn't going to work because we don't know what the context is and what the type is going to be. And so what we really want is something like this. We want something that in any context we can then read an expression, and it's going to produce another expression of some type that we don't know yet. This is right from some discrete math class that perhaps you took once upon a time. There exists some type, but Haskell doesn't do that. So instead, we have to use a continuation passing style. And here now we can use a higher rank type to pass this type in down there. And so that sort of gets rid of that problem. But it turns out that that too isn't quite enough. Because even in this type, we don't have enough information at runtime. And I can't really go into the full detail about that here. Oh dear, what's happening? I think my clicker has given up the ghost. Or my computer has crashed. My computer has crashed. Anyway, that's what the slide's supposed to look like. So here, this is the final type for it. What's cool is that we can do this at all. Is that we can actually build one of these things that are guaranteed to be correct at runtime, and there's sort of no conflict in doing that. Often when people start to see these more complex examples, you might think, well, gee, this length index vector is great, but I don't know the lengths of my lists before I've run my program. But actually, you don't need to. Using these techniques, you can learn this at runtime and still have it all type check. Okay. Let me pop ahead. So how do we evaluate in this lambda calculus? It's really easy. There's only one way to do it, really. As long as you have the basic idea of if you have a function and an argument, you apply the function to the argument, you sort of can't get it wrong. The Brown indices make this hard, but anytime you try to make a mistake, the type checker stops you from making that mistake. And so this was much easier. I've done this without the type checker helping me and gotten it wrong many, many times. And here, it took a while to get working, but once it type checked, it worked. The other thing that's implemented, just to prove that this works in a non-trivial setting, I have an optimization implemented in Stitch. So it does common-subexpression-elimination. So it looks for when you repeat the same thing twice, and instead it will let bind that and evaluate it only once. And it was the same thing. It was this beautiful thing that all I had to do was just keep writing code until it type checked, and then it worked. There's a little bit more to it than that for something like common subexpression-elimination. But the hard parts were taken care of for me. So as part of that, I actually use hash maps under the hood because we need a way of looking up to see if there's two expressions that are similar. So I use a hash map for that. And I had to generalize it to an I hash map that's indexed. But it turned out that was actually really easy. There's about 2,000 lines of the unordered containers library that I had to change, and it took me about an hour. Because all I had to do was make a change in the definition and then just follow all the type errors. It was the music that you hear when you do refactoring in a type language. It was fantastic. Okay, if we wanted to write instances, we'd need these quantified class constraints. We're going to skip over that. So conclusion here, we can use fancy types now in Haskell programs and do practical things. Right? This, in the end, is meant to be a practical program useful for teaching lambda calculus. I will be teaching lambda calculus next year. I will be using this, not teaching the internals, all of this stuff, but it's a good tool. It's a practical tool. So it's good to be fancy. So some people might know that I do a lot of work with dependent types, and I'm trying to implement dependent types into GHC. I want to announce this is ongoing work. It is active. We are making progress. Stephanie Wyrick and I have a grant. We are actually funded by the NSF to make dependent types into GHC, which is pretty awesome. So I have a bunch of summer research students, and I have to comment, I didn't do an exact count, but I think my summer research group has more women than there are in the room right now, so we have some work to do on that front. But hopefully some of these will be in this room very soon. So we have some specific goals for the summer. I have a research leave coming up. That's when a lot of work will get done. And then wouldn't it be great if I could merge? Pi is the dependent quantifier, so maybe I can merge on Pi Day. If you want to help, please come talk to me, and thanks very much.